And another very important phenomena of the light is, in fact, the interference phenomena of the light. So, because it's a wave. So let me give you an example. So you like Jumbo or Avalon, and you see the shell has a beautiful colors and which is changing. And you know what? This is coming from the interference of light. And also another good example is a soap bubble and soap film. You remember when you're playing with this, you see this beautiful rainbow-like color, and it actually changes because the thickness are different. And in fact, the thickness of this soap film is so thin such that it's comparable with the wavelength of the light. And then what happens is when the light enters this film, it always, as I said, when the wave meets an interface, it directly reflects, or some part will be transmitted. But usually there's a double layer because it's film. The next one, again, it's reflected or transmitted. And those reflected too, the differences of the phase will create a beautiful interference, such as this. When the distance between they match the phase, they will be so-called constructively interfere. When they're out of phase, the amplitude, a net amplitude will diminish, and we call it as destructive interference. So that's I depicted here, wave A and B. So wave, very important parameter is not only wavelength, but also the phase of them. So if they are in phase, if you combine them together here, then you have increased amplitude. So it will show in your detection a higher signal or a higher, more brighter. On the other hand, even the waves are there, but when they are this off the phase, then the combination will give a decreased amplitude, and that will give you a destructive interference. And so interference of light is very fundamental to give us very precise measurement at the range of this wavelength, such as several hundred nanometer detection. Even smaller than that is being possible. So this is such a sensitive technique we can utilize interference of the light. So one example is actually white light interferometry of lipid layer. So we are talking about biomedical engineering. So let me give you one example of how light interference may be useful for humans. This is our lab's research, so I brought this one. So we can use white light. So white light contains RGB at least, okay? So it's about ophthalmology. Our eye, you know, you have a tear in front of your eyeball, a cornea, and the tear is so thin that it will easily evaporate. The reason why it doesn't evaporate that fast is because we have also lipid layer, which is coming from the gland in your eyelids inside. So whenever you blink, you're oozing out this oil to coat on top of this tear layer, which is only about the order of tens of nanometer thickness. And this become a very interesting, important parameter for listening to ophthalmologists, because there are so many dry eye patients are there, and we want to diagnose whether do they suffer dry eye due to first poor tear production, or tear production is okay, but poor lipid layer. So to figure this out, in fact, our collaborating eye doctor create an interferometry, and we actually have analyzed this for dry eye syndrome. So let me show you quickly what this looks like. So there's a patient, and we provide a white light LED, like underneath of the human patient with this so-called slit lamp microscope. Then what it does is the white light goes to the eye, and the lipid layer will create thin film interferometry. Okay, and we want to focus that reflection of this white, and the white doesn't show up white anymore, depending on the film thickness. And so that with the color camera, we can calculate the thin film interferometry that this color corresponds to, let's say, 80 nanometer. And this color corresponds to 100 nanometers. This way, we can have two-dimensional map of this reflective. And we can automatically calculate, hey, your patients, you have this distribution of a lipid layer, which is so small, then you may be suffering from lipid layer lack. So we need to provide you proper treatment. So let me show you one movie describing this. So hopefully you can understand. So there's a lot of techniques, image processing here. So original video is here, and then you choose the center of the eye, and this is the reflective part. So you need to have also color has to be compensated, and these colors corresponds to thickness, and we have this blinking system. And show. So what it means is you have an original image, and you see this reflection of white light LED, but in fact, this one contains the room light, bluish light. You have to subtract those, and then you process only this part, and you compute these ones. Each of these pixels, you calculate the thickness of the lipid layer, and you calculate. So after blinking, the thickness goes diminished, but the average thickness, you can calculate the mean and standard deviation. And also at the same time, you can see the distribution of the thickness, as here, x-axis is this the thickness, y-axis is frequency. So you can see the overall distribution of the lipid layer. This provides the doctor a critical quantitative information for a more accurate diagnosis of dry eye syndrome. So I hope this one, this is coming from the interference nature of the light.